All right, hello everyone. Welcome to the first part of the video for section 4.7. We get into some what are called applied optimization problems. And before we jump into this, I just want to say that for the homework for this section, that's something you'll want to start as soon as possible. The problems in this particular section are quite lengthy and difficult and time consuming. So the earlier you can get started on them, the better. Okay, so let's jump into it. So as I said, this is applied optimization problems. And let's look at a problem that our good friend Queen Beyonce needs our help with. And I told her we'd have an answer for her soon. So let's get right into this. So she's in a quandary. She currently has 1,600 feet of fencing to create a pen for her private collection of sheep. She has decided to build the pen at one of her riverside properties so that one side of the pen will be bordered by the river, so she doesn't need to have a fence on that side. And we want to figure out what dimensions the sheep pen should have so that its size is maximized. So to approach a problem like this, the first thing we should do, since this describes something happening in the physical world, would be to draw a picture. So I'm going to draw a picture here. This is going to be my river. And she's building the pen, which does not say, but we do want to assume this is a rectangular pen. So it's going to look something like this, although I'm going to do that in a different color. Let's say it looks something like that. Okay, and even though I drew the river kind of wavy, we do want to assume that this fourth side here is a straight line, something like that. Okay, and then I'm going to label some parts of the fence. So I'm going to call these vertical sides here X. And notice that since it's rectangular, if that right-hand side has a length of X, then the left-hand side also has a length of X. And then based on the information we're given, notice that it says she has 1,600 feet of fencing. We've said that these two sides here have lengths of X. Based on that, what would be the length of this side in terms of X? Well, notice that, again, the total here, total amount of fencing we have is 1,600. And to figure out how much is left over for that third side, well, we have to subtract the amounts that we've already used, which are X and X. So it looks like that third side would have a length of 1,600 minus 2X. Okay. So this length here will be 1,600 minus 2X. All right. Let us then continue from there. So now we're trying to maximize the size here. And if we're trying to maximize the size, being that we already have information about the perimeter of the fence, the amount that we can have around the outside, to maximize, we'll probably want to look at the area. So I'm going to create a function that I'm going to call a of x. And how would we find the area of this pen? Well, it's a rectangular shape, so the length, or the, excuse me, the area would be found by doing length times width. And in our setup here, our length is 1,600 minus 2x. And our width is x. And if we distribute that in, then we get 1,600 x minus 2x squared. And that will be our area function. All right, and the next thing we want to do, well, first of all, we're trying to maximize the area, right? So hopefully your brain immediately goes to, we're going to take some sort of a derivative here, because we've been talking about mins and maxes with the relation to derivatives. But before we do that, let's also find some bounds on what the value for x could be. Okay, so let me again write the equation here. So 8 of x equals 1600x minus 2x squared. Now notice, right, what is the smallest value theoretically that the values for x could be? And really when I say x, we're thinking about for the small, so think about what these widths here could be, right? Because they could be something like 1 foot or a half a foot or a quarter of a foot or an eighth of a foot, but really the smallest they would ever be, I think, is 0. In fact, they would probably never actually be that small because then there wouldn't be a fence on that side. So we'll say that that's less than x. And then what's the largest they could ever be? Well, looking up here at the length, notice that if x were to equal 800, what would that width or that length there be? Well, it would be 0, right? So it looks like the largest x could be is 800. In fact, not sure it could actually be that length. We'll put it there anyways. All right, so we're just going to keep that in mind as we go about now trying to find the max or the min. So we'll first now take the derivative. So we'll do a prime of x, which using our power rule give us 1600 minus 4x. We know to find a min or a max, we need to find a critical value. So we'll set that equal to 0. So 0 equals 1600 minus 4x. And then if we solve that, I believe we'll get x equals 400. Right? Okay, so that's where our critical value is, and that's a candidate for where the max area could occur. So if you remember, one of our techniques for identifying maxes or mins is to now take that critical number along with the endpoints of our interval here and plug them into this original function here and see which one gives us the largest area. And in this case, it might be obvious which value this is going to be. Let's still check them. So I'll do a of 0. If I plug 0 in up there for x, I'm going to end up with 0, so that's probably not our max. If I plug in 400, I'm doing this in my calculator, I get 320,000. And this is feet squared. I should put that on there too. And then if we do the max value there for x, the 800, I believe we're going to get 0, but let me double check that. Yeah, we get 0 as well. So in this case, we see that that max value happens there at that value in the middle, the 300 or the 400. Now, we're not done with this problem because we've identified that the optimal value for x is 400. So I'm going to write that actually over here. But notice the question asked. The question asked, what are the dimensions? Right, so we want to know what the length and the width would have to be of our pin here. So to do that, we need to take that now and plug it in for each of these values. Width, excuse me, we see that that's just going to be 400 because that's the value for x. And then for the length, 400 feet, I should say. And for the length, then we plug in 400 there, so it's 1600 minus 2 times 400. And so that would give us 800 feet. Okay, so our optimal dimensions here would be 400 feet by 800 feet to give us that total area of 320,000 feet squared. Cool? All right, Beyonce will be very pleased. I will have a conversation with her and let her know we were able to figure this out. And on that note, in case you were wondering whether Beyonce actually has sheep or not, I just want to show you that I did not make this up. Okay, here's a picture of her taking care of one of her sheep. So just so you know, this was a real thing. All right, so let's talk about general problem solving strategies. So just like with the related rates problems that we did, okay, there's no way I can show you how to do these problems every single time and say do this like we do with the power rule. But there are some kind of general approaches we can take to solving them. So first one is to introduce variables. To introduce variables and draw a picture, and I would say in almost all cases drawing a picture is going to be helpful. Determine what you're trying to maximize or minimize, and also what range your variables could take. So that was an important step of what we did just a minute ago, when we found that range for x to be 0 to 800, and that's important for a couple of reasons. Number one, it's because your max or min could occur at one of those endpoints, even though it didn't on the last one. And the second thing is that if you get a value that is outside of that range, after you take your derivative and set equal to 0, then you know that that value doesn't work. Okay, so like on the last one, if we had set our derivative equal to 0 and gotten x equals 900, well, we automatically know that's not a candidate to be where our max occurs. All right, then we want to write a formula. So that's what it was. For example, we found the area formula on the last one. And when possible, you want to try to write your formula in terms of a single variable. Sometimes you may have multiple, but you want them to have in terms of single variable. And identify the domain. We kind of said that earlier. But yeah, that's an important step that we did. And then locating your maximum minimum, which, as it says here, that involves looking for critical points and evaluating the function at the endpoints of your domain. Okay, so let's look at another example of this. So let's say we have a piece of cardboard that's measuring 9 inches by 10 inches. And again, this is a rectangle. And so actually, before we go any further, I'm just going to draw that. So let's say there's that and that. Okay, so this is going to be 9 inches by 10 inches. And we're going to form a box with this by cutting squares with size length x from each corner and folding up the sides. So maybe you've seen this before. It's a common thing to create a box or an open top box from a rectangular piece of cardboard or something. So we can cut out corners here like this. Okay, and we're going to label those corners all having dimensions x by x. All right, excuse me. And what we want to do then is figure out a formula for the volume of this box. And again, you may have to do some three-dimensional visualization here of what this is going to look like. And in fact, I'm going to try my best to draw what this would look like after we fold it up. So let me see if I can do that. Oop, that was bad. Okay, and in this picture that I've drawn here, So this side here, that's going to correspond to that when it gets folded up. So those two things will get together. This side here will correspond to this lower side. And then this side here will correspond to this longer side here. Okay? And what I want to do on my box picture there is label what those lengths are in each case. So first of all, that originally this whole length was 9 inches, but the piece that ends up on the box there is just this piece here. And what will that length be? Well, it's going to be 9 minus each of these little pieces we've cut out, which each of those little pieces there have a length of x. So it looks like that length would be 9 minus 2x. So that's going to be this here. And using similar reasoning, we know that this whole length here was 10. We subtract a piece of x out of each side, so we know that orange piece there is going to be 10 minus 2x. So this is 10 minus 2x. So our volume formula then, if you remember to find the volume of a box like this, you multiply length times width times height. So we do 9 minus 2x times 10 minus 2x times x there. Okay. And I believe if I multiply that out, what we end up with is 4x cubed minus 38x squared plus 90x. Okay, and you guys can double check that for me. All right, the next thing then is to find a range of possibilities for x. Let's see if we have any restrictions on what x can be. And again, I'm going to kind of do this by inspection, but you could do this by doing some calculations. But notice that here, we have this 10 minus 2x, and the smallest that could ever be is really 0, which would happen when x equals 5. Similar for this 9 minus 2x, but that's when x equals 4.5. So that'd be kind of like the largest I think x could be. And the smallest, well, that would be whatever the smallest value for this height here could be, which again would be 0. So it looks like we have a range of 0 to 4.5 for our values of x. Okay? All right, and as you can imagine, when we're going with this is we want to try to maximize the size of the box. So that would be the next thing, is to now find a value of x that will maximize the volume of the box. They want us to give our answers with at least 3 decimal places. So to do that, we'll start with our volume equation here. The 4x cubed minus 38x squared plus 90x. Okay, we can take the derivative there. Should give us 12x squared minus 76x plus 90. Okay, and to solve that, unfortunately, I don't think that'll factor nicely. So we'll have to use our quadratic formula. And I'm not going to show all the work for that, but I'm going to write down the answers. Okay, so we're going to use the quadratic formula, like I said, and I forgot to mention that we first need to set this equal to 0 before we do that. And again, I'm not going to show all the work for the quadratic formula, but when we do that, I believe what we get is x equals 4.757, and 1.577. You can double check me on that. So those are both candidates for where a maximum volume could occur. And actually, let me just clear this out. So recall that we have this bound on x that it has to be between 0 and 4.5. And we just found these values. X equals 4.757 and 1.577. And notice that the 4.757 is outside of the range from above, so that's not a candidate for where the maximum could occur. So our candidates then will be these input points here, 0 and 4.5 and 1.577. Plug each of those into our volume equation. And 4.5. Let's see what we get here. Okay, and after putting each of those values in the calculator, we get that this is 0 inches cubed. This one is 63.114 inches cubed. And then the 4.5 also gives us 0 inches cubed. So we see from that that our maximum is going to occur here when x equals 1.577. Okay? All right, thank you guys for watching. That's all for now.